Okay, over to Professor Prakash P. Neelakandan.
Thank you, sir, for the kind words of introduction. And I would also like to thank the organizers for inviting me here, and also for the very wonderful hospitality. And this is like the photograph of my institute from where I come from. It's Institute of Nanoscience and Technology in Mohali, or like Chandigarh. It's a dedicated institute for research into nanoscience and related science. So this is a unique place with respect to like science, because we don't have conventional departments in our institute. Rather, we have different research groups. We have all sorts of faculty members having different backgrounds like physics, chemistry, biology, and even engineers. So all of us share the same space, and we have multidisciplinary or like interdisciplinary projects going on. So before moving on, let me give a brief introduction about like what we do in my research group. Basically, I'm trained as a physical organic chemist, having interest in photochemistry of organic materials. So these are the three kind of different projects that is presently going on. So the first one is today's discussion. I will come to that later on. The second one, what we do is like, like Prof. talked about nano clusters or like gold nano materials. So we have these gold nanoparticles, and if we have certain organic chromophores having matching optical properties, if they come in like close contact, if they are in the vicinity, their electronic states couple, and that leads to various new properties. So we explore such properties using various spectroscopy properties, and through collaborations we try to see whether they can be used for certain applications. Mostly we are into photodynamic therapy and like imaging of cells. The last one that is about synthesizing new organic compounds which resemble natural DNA bases, and we try to put them onto natural, the DNA strands, and again study their properties. So before we move on, I want to acknowledge the students who have done all the work. These are the present members who are working in the lab, and the others have kind of finished. And the names who I have shown in blue color, those are the ones who have contributed for today's talk. And I also acknowledge the contributions of my collaborators who have helped in various experiments and like data analysis. And also funding from various agencies are acknowledged. Now, coming to today's topic, electronics. Okay, don't get me wrong, I am not an electronics person, and we don't get into like device fabrication or anything like that. But our long-term objective is to have flexible electronic devices. So the question is like, why flexible devices? So like the electronic devices, like in the very old days when we started with electronics, everything was so big and bulky, right? So the initial interest or the topic in the area was to do miniaturization. That we succeeded in several ways, and we have very tiny devices these days. And now the present trend is to have flexible devices. So what is the need for flexible devices? Then it is kind of more useful. Like for example, you have these flexible displays which are already in the market, say in mobile phone displays, or like even flexible TVs are there. And it is also useful for wearable electronics, which can be like for various biological applications, wearable skin, etc. So when it comes to flexible electronics, then the regular material, that is silicon, that is used for the conventional electronics, they are having a little bit of disadvantage because they are not flexible. So they are always rigid, and then we need special techniques to kind of make them like we have to imprint them on flexible polymers or stuff like that. That comes with their own challenges. So in this way, organic materials are useful for this aspect, because organic molecules are inherently soft and flexible, so they can be used for this kind of applications. But again, organic molecules usually they lack the stability to kind of to kind of be stable. And as again Prof. was saying, right, like anything you make for practical application, they have to be used under variety of conditions. So organics are kind of little disadvantages in that way. And in this way, conjugated polymers are much better. Like probably you all know about the Nobel work of Alan Heeger and others. They developed these conjugated polymers, and they have been found very useful for these kind of applications. But again, polymers are a little difficult to synthesize and then further characterize, or functionalize. So in that way, again, we come back to organic-based materials. And in organic materials, single crystals are much better, because like in crystals, you have highly ordered packing, and because of that, the defects are almost absent, and that leads to a lot of good properties like absence of grain boundaries, or like better conductivity, or all those optoelectronic properties that are needed for these electronic devices. So that way, small molecule based single crystals are always better, and organic molecules are easy to synthesize, and then functionalization is always easy. Depending on the properties, we can have a series of compounds, and we can kind of tune them. But again, the problem is when you say again crystals, the thing that comes to our mind is something very hard and rigid. So how do you combine these? So a potential solution to that is flexible single crystals. So is it possible to have single crystals which have the advantages of better properties, and also have flexibility? So if I would have said this like say 20 years back, people would have laughed at me, because it's not possible to have single crystals which are highly flexible. But over the last say around 20 years, or like last couple of decades, Professor Desiraju and his group has pioneered this work, and they have clearly shown that it is indeed possible to have single crystals of either single organic compound or like multiple compounds which can have this flexibility. And flexibility means like when you apply a stress, they respond to that, they can be deformed, but they don't lose their crystallinity. And there are multiple types of flexibilities, like this is a simple brittle crystal which does not show any flexible features. The other one is a one-dimensional flexibility, say when you apply a load in one direction like this arrow shows, then it bends. And there is something known as plastic flexibility or plastic bending, which means it's an irreversible process. And there are also this elastic bending, where as soon as you take away the stress, it returns back to the original dimensions. That is like the elastic thing. So we have reached a stage where we can kind of design and synthesize organic compounds, where you can get single crystals of these compounds, and they can be deformed using a mechanical force. So this deformation can be in one-dimensional or multi-dimensional, like twisting or stretching, or all together. So our interest is in this area. As I said, like I'm basically a physical organic chemist. So we do synthesis of new compounds. We do alter their structures systematically, and see how that results in various type of properties, and how their properties are affected. So this is the simple strategy that we follow. Like this is one of the very simple reactions that anybody can see. It's a reaction between a simple aldehyde group and an amine giving a imine compound or a shift base. And we use salicylaldehyde based compounds because we have this additional hydroxy group, which can further aid in stimuli responsive properties. That means it can respond to an external input. And we are also interested in further complexing this compound with a boron. Boron, it's an electron deficient element. And when it complexes with this shift base, it forms a 5-membered or 6-membered ring, in this case 6-membered ring. And that leads to further changes in its electronic levels, which eventually transforms into a better optical properties. So by using this strategy, we have possibilities to use different amines. Say for example, if you use a flexible amine, you end up with a compound, something can be expressed like this. That will be a little bit of flexible. And if you have two rigid groups, then you can end up having a rigid final compound. And if you have multi-dentate compounds, we can even have macrocyclic compounds. So we are exploring different applications or different approaches in this way. These are some of the compounds that we have synthesized. So these are some of the aldehydes that we use. One is a simple salicylaldehyde. Other two are like derivatives of naphthaldehyde. And we have used a set of amines. So the first amine is a simple alkyl amine. Next one is an fluoro derivative of this, and then this is a diethyl aniline, and this is a pyrene containing group. So this is an aromatic group you have which is highly fluorescent, so that helps to tune the photophysical properties. So we have synthesized a set of compounds, and these are some of the examples. So coming to one by one, how the small changes in the structure, how that can lead to different changes in the properties, let us see. So these are the two first compounds, like denoted as 1B and 2B. The difference is the presence of fluoro groups in this. So when you have the fluoroalkyl chains, they did not form any crystals, rather they formed organogeles. That means like they were kind of, they hold the solvent and they form the gels. And having these fluoro groups, fluoride units in it, that helps to increase the hydrophobicity of these compounds, and they were found to be like highly hydrophobic and very close to superhydrophobic in nature. And they have this linear, fiber-like structures when we analyze them through various microscopic techniques. But on the other side, when we have these compounds like having this alkyl chain, you can see that they form single crystals, like these are the single crystals, and the interesting part was that they form flexible crystals. So these crystals, as you can see in this video, if you this is a crystal of this compound, and we have put it on a glass slide, and we are bending it using a brush and a tip of a pipette. So when you do that, as you can see, they bend, but at the same time they don't break. So they retain that bend nature, and again, like we have analyzed them through single crystal, they don't lose the crystallinity also after the bending process. And they are highly fluorescent, so that can have applications which I will show you later. Next. We simply added one more aromatic ring here from this, but as soon as this aromaticity or like the number of rings increased, the nature of the crystals changed completely. Now before we got much bigger crystals, and they were completely brittle. Like the moment you touch it, they simply break. They don't have any flexibility. So what we did, we changed this, we retained this core, and we changed the alkyl chain into a fluoroalkyl chain, and these are the imines and their boron compounds. So you can see when you have again this simple imine, they form like flake type of crystals, and they did not show any flexibility. But when you have this fluoroalkyl chain with the boron, then it formed very thin crystals, which are like even some centimeter long, and the width will be something like 200 or 300 micrometers in width. And this compound showed another interesting thing, like depending on the size of the crystals, they showed different types of bending, bending property. So thick crystals, that is anything above 0.05 millimeter in width, they were found to be plastic in nature. That means like if you apply a stress, they remain like kind of in a bend state. So this is again a crystal, like this is a tip of a forceps. We are like pushing it in one direction, and you can see that it retains that shape. But on the other side, this is the other crystal having, which are very thin, which is like having a width less than 0.05 mm. So when you push it, it bends, it will not break, and if you take out the stress, it will come back to the original state. And this you can do multiple number of times, and it, unless you apply a very high stress, it will not break. So what is the reason for this? So again, like we looked at the crystal packing of these compounds, and we can see that this is a crystal packing for this compound. This showed plastic flexibility, and this showed size dependent flexibility. So in both the cases, there are these planes which are running in this compound. So this is one molecule of this compound, and this is another molecule. They are arranged in a head to tail fashion, and this is one layer of arrangement. And between these layers, we have a slip, a plane running through that. We call it as slip planes. And that is true in the case of the other compound also. Again, like two molecules assembled, and there are these layers of dimers, and between these layers you have these planes in both directions in this case. And if you look at this crystal here, this showed completely brittle nature. There are no planes in it, like all these alkyl chains are interdigitated, and you don't get to see any planes in it. So the presence of these planes, they are very important for this bending property of these crystals. So that I show here using a schematic diagram here. So these are these dotted lines again show these slip planes, and when you apply a pressure like this, what happens? These crystals, they can slide or glide one over the other, and that pressure what we apply along this direction that will be absorbed by this. Anyway, this is not working. So that pressure is taken up by that multiple layers. It is dissipated along the layers. So they don't break. Instead, they just simply bend. And when the number of layers are less, that is the case of a thin crystal, you don't have several layers of compounds, the number of layers are minimum. And then what happens, like this pressure is taken up by this, and as soon as you take away the stress, it rebounces back. That way the stress is released. So that is the reason for the having the slip lanes is contributing towards the flexibility, and depending on the number of layers, we can have different types of flexibilities. Now, having these fluorescence properties, we have explored their little bit of applications for them. So this compound, like as I said, this is highly hydrophobic in nature. So we can make a fluorescent ink out of it, and you can see that this is a paper like black colored paper. You don't see anything under normal light. But we have made an impression using this as an fluorescent ink. Under UV light, you can see it very clearly. And this kind of markings can be made on different surfaces like paper or even granite or wood. And on the side, you can see that we have written the name of institute. Under normal light, you don't see it, but under ambient, under UV light, you can see. So these can be used for this marking or anti-counterfeiting applications. Like in currency notes, we have seen like people look at the UV light, right? In the same way, this can be useful for these applications. And these other compounds which were forming these flexible crystals, they can be used for optical waveguide properties. So what are optical waveguides? You know, like optical fibers, right? It's exactly a similar thing. So if you kind of use this crystal as a light propagating medium, if you shine light at one tip of this compound, so this arrow indicates that here we are showing a light, and this travels through the crystal and it comes at the end. That is why the end tip of the crystal is highly glowing. So these crystals can be used for this waveguiding applications. And there are two type of waveguides can be done. That is, one is active waveguiding, another passive waveguiding. Active waveguiding means these compounds are inherently fluorescent. So that fluorescence emitted by this compound will be transmitted to the crystal, and it can be kind of received at the other end of the crystal. And passive waveguiding is something where a light which is not at all absorbed by this sample, that will be also transmitted. So that we have shown both blue as well as red lights can be used for this. So you know, these are like very fundamental things we have done. But you know, like there are optical data transfer cables, etc. So these crystals may be useful for such applications. We have not explored it yet. We are in the process of kind of collaborating to see whether it can be used for such applications. Now moving on to next set of compounds, where we have changed from the alkyl or fluoroalkyl chains, that is from the flexible chains, to a rigid compound. So we have synthesized two compounds, these 5B and 6B. The difference is that the position of this hydroxy group and the aldehyde group. So here the hydroxy group at the second position, here is at the first position. But such a small change, you see, you can see that from the crystals, they lead to a like very major difference in the color. So this is, they formed, this compound 5B formed two polymorphs having orange and red in color. The other one formed more reddish kind of compounds. These compounds were not flexible in nature. You can see they were just brittle. I don't know, it's not, yeah. This is simply brittle. I think that video is not working now. But it simply breaks. When you apply the pressure, it does not take the pressure, it breaks. But other interesting property that we see is that this is a DST curve for these compounds. If you look at this compound 5B, before the melt, this is a melting transition. Like when you heat the sample, what happens? It melts. So this is the melting transition for this compound. But before the melting transition, there are these very small or like spike-like features, which is completely absent in this compound. So we wanted to know what is going on here. So what we did was we looked at this process, like heating this material under a microscope. So this is a hot stage microscopy video for these compounds. Yeah, so you can see This compound, when you start heating it, say above around 110 to 120 degrees, slowly it starts to change color, and then it breaks, and some of them even bends. So we see all these features here. Color change will be there. Some of the crystal moves away from the focus of the microscope. Some of them crack, some of them split, and then expansion, explosion, all these properties we see. In the case of the other polymorph, we don't see all these properties, but mostly color change and little bit of movement we see. And if you look at the other one, the other isomer of the same compound, nothing happens. Like if you heat it from 50 degrees to 260 degrees, nothing happens. It remains exactly the same. No movements are there. So what is the difference between these two compounds, or like these polymorphs including? Why some of them are showing why one compound is showing the physical movements as you heat, but not the others? So again, to understand this, we looked at the crystal structure for these compounds. So we can calculate what is known as quinoid character. So that can be calculated using this equation, where A and B stands for some of these molecular dimensions which can be obtained from the crystal data. So as you see, as we change from one isomer, one polymorph to the other one and to the next compound, this value changes. So that shows that, so this is the quinoid isomer, or like the quinoid form of this compound. As you see, depending on the molecular parameters and the packing, there is varying degree of quinoid character for these compounds. So quinoid character means like this ring will be either planar or kind of at a particular angle with respect to the remaining of the compound. So because of that, there is a strong interaction between nitrogen has, this is a nitrogen, it has a lone pair of electrons, so that can interact with this part here. Here you have the boron, which is electron deficient. So that interaction will be affected depending on the planarity of the compound, because like conjugated molecules, it allows like electron delocalization. So based on that, we can explain the difference in these properties. So wherever you have a strong charge transfer properties, we don't see it's kind of that don't respond to external stimuli. But when the charge transfer is kind of a little less intense, then we see this in response towards temperature. And apart from this, in solution state also, this compound show different colors, etc. Again related to this charge transfer property. So as you see, like depending on the polarity of the solvent, these are like highly non-polar solvent to highly polar solvent, we see a change in color. Basically this is a fluorescence color. And in acids, these are acetic acid and formic acid, they give completely different color. The reason is that when you have acid, this gets protonated, this amino group gets protonated, and that prevents the charge transfer property. And as a result, you get an emission from the monomeric form or the singlet locally excited state. Because of that, we see a drastic color change from say orange or reddish color to either bluish or greenish in nature. Now, this molecule, so because it shows response to acid and different polarity solvents, we could develop a test paper strip where we have simply, this is a simple paper coated with our sample, and if you expose it to acids like HCl or trifluoroacetic acid vapors, it changes color, and you can clearly see that using our visual eyes. And if you expose it to a basic paper like triethylamine, it goes back to the original state. And the crystals also do something similar. I did not show for the acid vapors, but it shows, as I showed in that microscopy video, it responds to temperature. And you can see this is the top one is the normal ambient light. This is under a UV light. So here you can see like this is only one compound, but this is a mixture of two compounds. So here you can see under normal low temperature, there are two colors are visible, but when you heat it, all of them change color. So this again can be used for say security applications. So if you can imprint these crystals into say some kind of a material or document, and you heat it a little bit, then you can see that like there are different color patterns are developed. So this can have that kind of applications. Now, moving on to another compound, like here again we change to a much bigger group which having a fluorophore in it. So this compound we did not, this is with the shift base, not with the boron compound that I showed earlier. So here the advantage is that you have this site here having a hydroxy group and this nitrogen here that can bind to some external material. Say if you have some kind of a input added, it can bind them. So what we have studied here, like so initially this is the photograph of a crystal. You can see it forms, it can be bent. It shows elastic bending. That means if you bend it and take out the force, it will go back to the original straight form. So, and we also calculated the bending strain. And when you expose it to acid vapors, what happens? It becomes more flexible. The bending strain increased from 0.7% to 2.8%. And the color also, if you see, it intensified a bit because the acid probably protonated the imine there. And as a result, you end up with a little better fluorescence here. But if you treat it with copper, that means like we took this crystal and dipped it in a solution containing copper. And when you take it out, it loses its flexibility completely. And the fluorescence is also completely gone. So the similar way when you try to bend it, it simply breaks it. So I don't have videos, but it simply breaks. I can see the photos. And we have also looked at the surface of this compound using SEM. And you see like when it is in the pristine state or after treating with acid, it has this smooth surface. But when the copper is, we have treated it with copper, copper is probably deposited on the surface. And as a result, it forms this kind of rough surface. So probably that explains the brittleness of these crystals. So this is again the crystal packing, and you can see from this crystal packing, again there are, this is one molecule, this is another molecule of this compound. So they have kind of an interlocking kind of a structure, and in between there is a void or a cavity where probably this metal ion and the acid can bind. So we assume that this is a surface modification, and when you dip the crystal into solution of copper, the copper gets deposited on the surface. That's what we are showing it here. And but because of the deposition, it breaks it interrupts various intermolecular interactions that are present in the crystal structure, which holds the molecules together. Because of that, it breaks the crystal. So this same crystal, we see that there are multiple, it gives different outputs when you have different inputs, right? So this forms the basic of molecular logic operations. Like molecular operation, like logic operations, you know, like 0 and 1, that is a basic input and output. And that forms the fundamental of most of these electronic devices, like computing, etc., right? So we have tried to create a circuit for molecular logic operation using this. So we have multiple inputs here, like compound, the crystal of the compound itself is the input 1. And when you have copper, that is input 2, and acid is the input 3. And we have multiple outputs, that is the fluorescence and the bending properties are the multiple outputs. So when you have crystal 1 as the input, then the output is emission and flexibility. Sorry, this is wrong, it should have been 1 here. So we get an output, input as 1, outputs as 1 and 1. But when you have crystal and copper, the output is all 0 because none of the features are there. It loses the fluorescence and it also loses the flexibility. So that way, we have shown that by using different inputs, we can get a different output. That forms a fundamental principle for molecular logic operations. So finally, there is one more final, this is the final slide. So this is a recent work that is going on. So as you can again see here, this is a compound that we have synthesized, different from the other ones. So this again binds to 2 different cations and anions, like zinc 2+ and fluoride anion it binds. And when it binds, you can see that the color changes. So that again depends on the binding of the material onto the surface of these compounds. So we end up with different materials. And the interesting part of this crystals is that we get different surface charges after binding of these metals. So this is a Kelvin probe force microscopy images that measures the surface charge on these crystals. So when we measure these, we can see that when you coat the crystal, like the pristine crystals, what we start with, they are like close to zero or like a little on the positive side. But when we coated it with crystal, the charge increased to almost like 500 millivolts. But when it is coated with fluoride, the charge becomes like kind of minus 200 millivolts. So the same material, depending on the treatment, it is giving different charges. And one more interesting feature of this crystal is that, like you can see, these are the two individual crystals. And if you take, we have now three crystals, one starting pristine crystal, one coated with zinc and one coated with fluoride. If you pick any of these two combinations, any of two from these three, and you kind of keep them on the top of it and you shine light on that, certain chemical reactions, probably tautomerism happens with this, and the crystal join together. And this is very kind of unknown or uncommon, and this is very interesting, and you can see this video here. So that's a crystal at the tip, like this is a place where it is joined together. We are moving it using a brush, but still it is not moving, and you can even hold it like this. It will not break. It will hold the weight of the crystal as such. It will not break into the individual ones. But if you apply too much of pressure, you can see at the end, if you use like both sides, if you try to put the pressure, then eventually it comes apart. And the same thing is shown in these other photographs, where you can see here one crystal is on the top of the other. It's also same here. So we have, this is again kind of a very recent results, and we are in the process of kind of creating a circuit where these crystals can be used as switches. So because it can develop different charges depending on the surface coating, so we show that it is possible to even join them, so which can be useful for certain switching applications. So we are in the process of doing this, and this is done in collaboration with Dr. Kozhikode in IIT Roorkee. So they are working on building a circuit using these crystals. So with this, I will conclude my talk. So we have made a series of imines and their boron compounds, and depending on the structure, we can show that they form different types of packing and slip planes. Wherever you have slip planes, they can form these flexible crystals, and this flexibility and other properties can be tuned using various external stimuli. And we are in the process of kind of developing, we are seeing whether it can be developed into some sort of devices. And thank you for the listening.
Professor Neelakandan has described various properties and his research programs. Now, if you have got any queries about it, please.
Do you understand the molecular reason for that fusion?
It's still ongoing, but we feel it's some kind of a tautomerization between the imines. Imines are known to undergo tautomerization. So we feel, plus there is this electrostatic interactions between the different charges. We have not confirmed it. We are still studying it.
It's in the family of mechanical properties that you looked at, the packing-induced changes. You know, people look at these organic materials in the context of energy generation. Mechanical energy to electrical and conversion, mechanochromic effects, triboelectricity and different contexts. Do we currently understand the origin of triboelectricity? Can we design materials with specific objectives of this kind in mind?
I think yes. At least in the case of piezoelectricity, people have kind of come up with explanations, and molecules can be designed for that. Triboelectricity, I'm not much familiar, but I think it is possible.
Are you looking at this?
Not yet. Like some of these compounds, whatever we synthesize, we tried, but we did not get any positive feedback yet. So we are kind of modifying these structures, and we are doing that. So far, it's not done.
The last bit that you talked about molecular fusion and all, where is it going to be? It is going to be in the artificial healing or self-healing materials?
It's actually not healing, because healing means we start with something, we deliberately damage it and then heal. This is actually joining of completely two different things. So one thing that we are kind of seeing is that because of these different charges, probably some kind of a circuits can be developed, and also these charge gradients are useful for, again, for this energy harvesting. So that is something we are trying to explore. So that's my collaborator, he is into that. So we are doing that.
This is happening at the time scale of the photons? You said that is irradiation is required, right?
Yeah, it's like, I think less than a minute is good enough.
Thank you.
Whether the perfluoroalkyl chain has which lacks the van der Waals interaction. Is the reason for its peculiar behavior?
Sorry, is it?
Perfluoroalkyl chain you have. So it does not have the London dispersing effect because of the smaller size and the huge electron density of the fluorine atom. So that it cannot stack, unlike the normal CH2 bond.
Yeah.
CH2, CH2.
Yeah.
Is that reason?
Yeah, probably that is a reason. Like unless it, as you said, it cannot stack or like order in a ordered way, it will not form the crystal. That's what we are even seeing in the very first example where it forms the gel.
Okay. Thank you.
My question was kind of similar with this fluorine. Like I see most of this, what you have shown has this fluorine. So is it by design you have used, or is it by accident? Like if you used it by design, so what interactions did you expect it to have? Like even the two fluorines, if whatever this crystals, when they crystallize, they will have a difluoro kind of interactions, this kind of non-bonding interactions which will be there in those systems to let it crystallize. So how important is that effect, and what is the basic reason for it?
So these fluorines, like the BF2, like the fluorines that are attached to the boron, that we used it for optical properties. So when they kind of complex with the shift bases, they reduce the energy levels, and that leads to good fluorescence properties. So that was like our first interest. And the side chains, that molecule also we designed for, actually for some other reason, but this crystal part came out as a serendipity. But that we wanted to study because of these fluorine-fluorine interactions, as you said, like they have their own properties. That's what we wanted to kind of explore, but we ended up with these crystals having different properties. So yes, both fluorines, we wanted to have it deliberately, we designed it for certain reasons, but the crystal part was something unexpected. But the other fluorine, like the BF2, is as expected, it gave nice fluorescence and other related properties.
If you have other questions, please join me in thanking Professor Prakash Neelakandan for his wonderful presentation.